Hi, to the magic of numbers after the break. So in the last part of lecture, we figured out how to invent multiplication, which is super cool and all. But when we tried to solve an equation, we realized that we got stuck at the very end because we don't know how to divide yet. I mean, we know how to divide, but we haven't properly invented how to divide, and so we can't use it yet. So, well, now let's go back and think like a mathematician. So, like, this is going to be sort of a giveaway, but let's go ahead and get started with something nice and easy. So, which of these lengths do we not know how to compute yet? Okay, yep, yeah, so we don't know how to cut a rope in half. And so that's what we're going to do in this part of the lecture. We're going to figure out how to cut things in half, or cut things into thirds. So that's going to be the goal. And in order to do that, we need to invent something that we're going to call division, since we're cutting a rope in half. We're dividing it in half. So what is that mathematically, really? So if we're going to try to invent division, well, you might think back to addition and subtraction. So subtraction allows you to reverse addition. So what do we mean by that? Well, if you have, say, 5 plus 3 is equal to 8, what you've done is you've added 3 to 5. Well, then if you subtract, so 8 minus 3, you get back what you started with, the 5. So that gives us a hint about how we can define division. We can just define it as reversing multiplication. So if 5 times 3 is equal to 15, well, then we might say 15 divided by 3 is equal to 5. So that gets us part of the way there, right? So definition, if x times y is equal to z, then z divided by y is equal to x. But now, there's a bit of an issue with this. What about z divided by y when there doesn't exist an x such that x times y is equal to z? So, for example, what happens if we want 5 divided by 2? Well, 2 times 2 is equal to 4, and 2 times 3 is equal to 6. And we don't have any numbers in between. And so there isn't a number x such that this works. So, well, what do we do? So, let me reset the chat. So, is the answer, it's fine, we don't need all divisions to make sense? Or is the answer, let's invent more numbers? Or is the answer, all math is pointless? Or I'm going to give you a fourth option this time, which wasn't in last time. It's fine. The answer doesn't need to be a number. What if we invent non-numbers that we can divide things to? So let's see what people want to do. So most people want to invent new numbers, which is a very good mathematician-like way of thinking about things. And in fact, this is one of the big progressions in how number theory has progressed, is, well, we just kept on inventing new ways of having numbers. And that's sort of the point of it. It's not just studying the numbers we know, it's also inventing new ways of understanding numbers and new things that look number-like and that we can use as numbers even though they look slightly weird. And a few people are saying that, well, it's fine, the answer doesn't need to be a number. Maybe it can be like a pair of numbers, like, say, an answer and a remainder. So that's also another way of doing it. And so it turns out that the answer to this is actually going to be a mix. Oh, sorry. I keep on tapping into the wrong slide. It's actually going to be a mix of all three of these three. So we are going to invent more numbers. And we are going, but it's still fine for not all divisions to make sense. You know, in fact, we'll see this a little bit later when we try to divide by 0. You guys might have heard that you can't do that. And even when we invent more numbers, dividing by 0 is hard. And the other answer is, well, sometimes people can also do division without giving a single number as an answer, but maybe a pair of numbers or some other way of understanding the answer, of reversing this operation, even if it's not quite just another number. Okay, and so we got a good mix of the votes. And so, wait, do I really want to? Ah, yes. So we're inventing numbers. What kinds of numbers are we going to invent? We're going to be inventing fractions. So you guys might have heard of these before. So what if we simply define a new number by x divided by y is equal to x over y for all integers. So integers are positive or negative whole numbers, or 0, x and y. So what we're going to do is we're just defining new numbers that look like this. So please type in chat what goes wrong. So there are a couple of things that go wrong here. One of them I already sort of mentioned. One is that if y is equal to 0, weird stuff happens. Oh, okay. Sorry, can you guys hear me now? Welcome back. Humanity restored. Hopefully I'm not consuming too much humanity with this. I don't want to go hollow before my time. Welcome back. Let's go. Can't hear you. Can't hear. Okay, so I am now back online. Okay, so welcome back. Almost overthrown as host? Oh, well, that wouldn't be good. Okay, so welcome back, everyone. Let me make sure my recording is going. I'll edit all these things out for the recording later, but you guys get to see how the sausage is made. Okay, so I was waiting to see, please type in chat, what goes wrong? So if we simply define a new number by saying, like, putting two numbers on top of each other, so something we're going to call a fraction. So there are a couple of things that can go wrong. What are they? So anyone have any guesses? So I already mentioned one of them, which is that dividing by 0 doesn't work out properly when y cannot be 0. Yeah, so that is one of the things that goes wrong. Get a decimal number. So you're very much on the right track there. We're going to talk about decimal numbers a little bit later. Those are actually quite complicated. But the problem here is that numbers can now have multiple names. So what do I mean by that? I mean that so if I write down the number 4 over 2, well, we all know that's also the same as 0. Or 3 over 1 is the same as 3. Or things like 2 over 5 are the same as 4 over 10. So some of these are new numbers. This is a new number. This is not a number that we had originally, but some of these are new names for old numbers. So it's sort of like how I go by Professor Yu, I also go by William, I also go by Ying, and so like I go by a number of different names, and now when we've invented fractions, names can go, like we have a bunch of different things that our fractions can go by, or sorry, that our numbers can go by. We've given them more names. And so that raises the question of how do we know when two different names for a number mean the same thing? We didn't have that problem back when we were just dealing with whole numbers. Like if a number looked different from another number, then it was a different number. But now all of a sudden, you don't necessarily know that in advance. And this has to do with decimals as well. And decimals are another way of naming numbers. The other part, which was also mentioned, is that, well, the definition is inconsistent if y is equal to 0. So we don't allow it. So 3 over 0, suppose that we allowed that to be a number. Well, that would imply that 3 divided by 0 is equal to 3 over 0, where that's the name of the number. Well, if that's true, remember how we invented division. We invented this as the reverse multiplication, and so then that means that, so 3 over 0 times 0 is equal to 3. But we also know that everything times 0 has to be equal to 0. So, but 0 times anything is 0. And so you end up with this inconsistency. And it turns out that properly understanding what goes on here is actually really complicated. And you really need to get to calculus and limits to formalize, because we're really talking about concepts of infinity, things that are infinitely small or infinitely big. And so this is not a calculus class, so we're not going to make you do it, but just keep in mind that this is why we also said that it's fine, we don't need all divisions to make sense, we're just trying to make more divisions make sense. And you still do end up with a couple things, well, in this case, when the denominator is 0, that still doesn't make sense. We can't divide by 0. Any questions about that before we move on? No. Okay, great. So, well, what are two fractions, different ways of writing the same number? Well, let's do this in the abstract first. So, often I've been teaching this class by giving you concrete examples first. But okay, when mathematicians look at these things, we often look at these things super abstractly with x's and y's and z's. So if we have x over y is equal to z over w, well, one thing we can do is we know that division and fractions are the opposite of multiplication. So we can multiply this. X over y times y is equal to z over w times y, because we can multiply both things by the same number, and you get the same thing. So then x is equal to z over w times y, because it's the reverse. And we can also do the same thing to get x is equal times y. X times w is equal to z times y. Or similarly, 2 over 5 is equal to 4 over 10, because 2 times 10 is equal to 5 times 4 is equal to 20. Also, we get 0 over 5 is equal to things like 0 over 3, because 0 times everything is 0. And so the way we do this is when the numerator of one fraction, so that's the top, times the denominator of the other is equal to its denominator times the numerator of the other. So let's just decide that two fractions are equivalent. Cross multiply. Yeah, that's exactly what we're doing, right? So we're multiplying these things together to get that. Yep. So this is how we figure out that two things are the same. And another way of figuring out the same is eventually when we learn how to factor numbers, you can also write this as 2 over 5 is equal to 2 over 2 times 2 over 5, right? And 2 over 2, that's equal to 1. And so on, that is correct. And so there are a couple of different ways of doing this, but I'm just trying to get across that there are ways of showing that two fractions are the same number. And this really goes back to we just have different names for the same number. A number can have lots of different names. So now, once we've done that, well, with the invention of negative numbers, we could also reverse addition by adding a negative number. So things like 5 plus 3 is equal to 8. So then 8 plus negative 3 is equal to 5. And luckily, when we're dealing with multiplication, once we've invented fractions, we can also reverse multiplication by any x that's not equal to 0 by multiplying by 1 over x. You can't reverse multiplication by 0 because you've turned everything into 0, and so there's no way of reversing that. But for any other number, you can reverse it by multiplying by the reciprocal. So 5 times 3 is equal to 15. Oh, sorry, not 1 over 15. Is equal to 15. So that means that 15 divided by 3 is equal to 5. But we can also write that as 15 times 1/3 is equal to 5. And sometimes you will also write this as, so this also means that 15 over 3 is equal to 15 times, so like, these are all the same thing. But importantly, we can reverse multiplication by multiplying, for most multiplications, except for a multiplication by 0, because you aren't allowed to divide by 0. So now, well, now we have these new sets of numbers. Multiplication is sort of easy for fractions, right? You just do it for both the top and the bottom. But how do we do fractions and addition? How do we add together fractions? Well, what we can do is we can use the distributive property and reciprocals. How does this work? So you might have a 2 times 2 plus 5/3. Okay? So these are two numbers. We're adding them together. Well, there are a number of things we can do. And you guys might remember that you have to put all of these over the same denominator if you want to add them together. And one way of seeing that is by using the distributive property and reciprocals. So you have 2, this is equal to 2 times 1 plus 5 over 3, because that's just the multiplicative identity property, right? So this is just the identity. When you multiply by 1, you get the same number. So these two things are equal. And this is equal to 2 times, well, it turns out 3 over 3 is another label for 1. So this is a multiplication sign here. 2 times 3 over 3 is equal to 2 times 1. And we still have this 5/3. And, there are a number of different ways of writing it out, but I'm going to write it out in all its gory detail. So this means that 2 times 3 times 1/3 plus 5 over 3. Oh, sorry, I'm going to write that slightly differently. Times 5 plus 5, wrong color. Plus 5 times 1/3. Well, then this is equal to, and this is the reason we want everything in the denominator to be the same, because you can also think of this as just the denominator as being the same. You can also think of this as 2 times 3 over 3 plus 5 over 3. But the idea here is that we now have, we can go directly from here and get to 2 times 3 plus 5 by using the distributive property times 1 over 3. This is distributive property of multiplication and addition. And now this is equal to 6 plus 5 times 1 over 3, which is equal to 11 times 1 over 3, which is equal to 11 over 3. So this seems like an awfully complicated way of doing stuff that you already know, which is that you want the denominators to be the same. But this explains why you can do that. And you can add together numbers when the denominators are the same, or you can add together numerators when the denominators are the same, precisely because you can think of it as multiplying by a reciprocal. Did that all make sense? That went a little bit fast, but hopefully it's stuff that you vaguely remember. Okay, and so in some sense, this is pretty good, right? Because now we've defined a bunch of new numbers, these things called fractions. And so we've defined fractions, and that allows us to do a number of different things. So we've defined fractions, and now we can multiply and divide to our heart's content. Just a moment. What is going on here? Can vaguely remember that, but fractions are always question marks for you. Yeah, so there are a number of different ways of thinking about fractions, and we'll actually talk about a slightly different way of thinking about fractions again in a moment. But the basic idea is that because we've turned division and fractions are basically the same thing. Oh yeah, let me go to the previous slide for a bit. Division and fractions are basically the same thing. Oh, my confusometer is not working, so let me try to fix that quickly. Although we're getting near the end of class, so it might not be that big a deal. Today is the... Wait, why is this not saving? There. Okay, the confusometer is broken right now because there's something going horrendously wrong. So unfortunately, we will be without the confusometer for the remainder of today. Oh, no. Here. This should do it. Okay, so I fixed the confusometer. And okay, yeah, there was a big spike in confusion there, which I failed to see. But yeah, so basically the idea is that division is just basically multiplication by fractions. And because of that, when you're working with fractions, you can think of division by the denominator as just what you're dividing by. And so you can think of that as multiplying by the reciprocal, and therefore, when you're dealing with fractions, what you need to do is you need to make the bottom the same. And so if that's a bit fuzzy, you should practice that a little bit, because that is important, because fractions are an important part of, well, both this class and, well, real life. But if you don't like fractions, there are other things you can do as well. So for example, back when we were talking about the different things you could do, sometimes you might say it's fine, we don't need everything to be a number. And that's basically what we're doing when we're doing division with remainder. You're not actually going to have the answer be a single number. So for example, suppose that I am going to try to divide up 7 phones among 3 people evenly. Using fractions is probably a bad idea. So let's say I have several phones here. You're going to see my terrible drawing skills right now. 4. But I wanted to do something that was an actual real-world object. So you could see how this is a bad idea. My phones are getting bigger. But yeah, so suppose we have 6 phones, and let's say we have someone named Alice who gets, well, maybe Alice gets 2 of them, and maybe Bob gets 2 of them, and maybe Carol gets another 2 of them. Well, what do we do with the last phone if you want to divide them evenly? Well, one thing you could do is you could split the phone into thirds. And that's what you would do if you were using fractions. Phone's getting bigger. Yes, it is a true-to-life evolution. But yeah, so using fractions is a bad idea when you're dividing phones among people. Like, it might work well for like dividing cakes, because those you can cut in half, but you probably don't want to be dividing up your cell phone into pieces. I mean, maybe if you're an engineer, that makes a bit more sense, but probably generally not a good idea. So instead what you can say is, oh, sorry, my phone's got too big. So instead we can say that each person gets 2 phones with 1 phone remaining as the remainder. So what we say is 7 divided by 3 is equal to 2 remainder 1. Or another way of thinking about this is here division is still the opposite of multiplication except slightly different. So 7 is equal to 2 times 3 plus the remainder. So somehow division is still the reverse. But it's reversing it in a slightly different way because what you're doing is you're just adding the remainder on after you do the multiplication to undo it, instead of having it be part of the same number. And luckily, there is a nice connection between 2 divisions. So division with remainder and division giving fractions can be converted into each other because if we convert the fraction to an integer plus a fraction where the numerator is greater than the denominator, then the remainder is the numerator. So that was a lot of saying big words. What do I mean? Well, 7 divided by 3 is equal to 7 over 3. And another way of writing that is that 6 plus 1 over 3, which is equal to 6 over 3, plus 1 over 3, which is equal to 2 plus 1 over 3. Right? So that's another way of writing 7 divided by 3. Alternately, if we just do 7 divided by 3, that's equal to 2 remainder with a remainder of 1. And you can sort of see that these all make sense together because 7 is equal to 2 times 3 plus 1, or 7 thirds is equal to 2 plus 1 third. And so these 2 ways of doing division actually give you very comparable amounts of information, which makes sense, right? Because if you want to be able to reverse things, you need to have the same amount of information. But just one way of writing it is writing it as a remainder, whereas the other way, if you convert it over to a whole number plus a small fraction, we haven't shown that these fractions are between 0 and 1, but if you convert a fraction between 0 and 1, then you end up getting the remainder as the numerator of the remaining fraction. Okay, so even though we've defined division in 2 different ways, you actually get the same kind of answer. Okay, but now let's go back to what we started today's lecture with, which is the number line. So using the form from the previous slide, we can put fractions on the number line by using the remainder and even spacing. So for example, let's blow up this number line a bit. So let's say this is 0, and let's say this is 1, and this is 2. Well, where does, say, 7/4 go on this number line? Well, you can rewrite this as 1 plus 3/4, or 1 and 3/4. And so then what we want is, we want there to be 4 even spaces and 3 ticks, third tick. So 1, 2, 3, 4. So this is 4 even spaces, and then this number goes there. And you also have like 5/4, 6/4, and that would be 7/4. And note that this is another name for this is 3/2, because this is also 1 and 1/2. Okay? So we're able to put fractions on the number line by just using the fact that it's some number plus the remainder, and then the remainder takes up some portion of the space to the next big jump. And so this allows us to do things that are in between 2 different whole numbers. And mathematicians give these things funny names, and so any number we can write as a fraction we call a rational number, which is just a fancy word for saying a number that can be written as a fraction. So let's try it out. Let's have you guys solve a linear equation. So you'll notice that this is the same. So those of you who've already been in tutorial, so I know some of you have Tuesday tutorial, and so those of you who've already had tutorial have probably already covered a little bit more of, we have a really good question. Is any number then technically a rational number? No, it is not, and we will get to that later in this class. Because, so one way of thinking about it is, we've been inventing new numbers when we've been inventing new operations. So we invented negative numbers because we needed them for subtraction. We invented rational numbers because we needed them for division. Well, next time, so on Monday, we're going to be talking about powers and square roots, and like roots, powers and square roots, cube roots, and stuff like that. It turns out powers don't mess things up, but when you take a square root or a cube root, then those numbers aren't rational. And you have to invent another set of numbers. And like this can keep on going. So like every time we invent a new operation, you have to ask yourself, are my existing numbers enough, or do I need to invent a new number? And it turns out that we're still not done, and you can keep on inventing new numbers. There is some limit to, I mean, there's not really a limit to how many new numbers you can invent, though there's some practical limit to how many are useful. Okay, so it looks like people are guessing B. Well, let's work through this slowly. So instead of asking about what property you're using, I'm just going to use the properties, but say what I'm doing to both sides of the equation. So what am I going to do first? So the first thing I'm going to do is I'm going to add 3/8 to both sides. So then I'm going to get 1/2 x, well, minus 3/8, but if I add 3/8, those cancel out and that just becomes 0. This is equal to 3x over 10 plus 1/8 plus 3/8. But of course I can combine those, and so 1/2 x is equal to 3x over 10 plus 4/8. And there are a number of things you can do here. So if you recognize that 4/8 is 1/2, that's the easier way of going about it. But now let's suppose that sometimes it's hard to recognize that that's true. So let's do it without recognizing that 4/8 is 1/2. So then what we're going to do next is then we're going to, oh, no, this is super important. So remember, this is why I was going through this carefully. So 1/8 plus 3/8 is equal to 1 times 1/8 plus 3 times 1/8, right? So then, when you're using the distributive property, you get 1 plus 3 times 1/8. So you don't ever add up the denominators. And so that's equal to 4 times 1/8, which is equal to 4/8. Okay, so that's actually very important, and one of the reasons why you have to be careful with these things. There's another question. Why did you pick 3/8 to add on the other side? Mostly because I wanted to cancel this out. I wanted to, so you might have heard of people moving things from one side of the equation to the other. Like, you don't really move something from one side to the other, but like that's sort of what you're doing when you add 3/8, because you're canceling out the minus 3/8. Okay, but let's keep on going. So if you knew that this was 1/2, that would actually make this a lot easier, but sometimes it's hard to recognize those things. So if you were to recognize that, that would make life easier, but let's say we don't recognize it. So what we're going to do now is let's multiply by 8. So let's multiply by 8. Let me do this in a slightly different color. So multiply by 8 on both sides. Well, what's 8 divided by 2? It's 4, right? So you get 4x is equal to 24x divided by 10 plus 4. Okay, and I'm going to say that maybe you do recognize that 24 over 10 is 12 over 5. So then you get 4x is equal to 12x over 5 plus 4. And then for the next step, you notice that I have x's on both sides, and I only want all the x's on one side. So what can I do? Well, I can subtract again. So I'm going to subtract 12x over 5 from both sides. So that gives me 4x minus 12x over 5 is equal to 4. Okay? And then, well, let's multiply both sides by 5. Let me use the distributive property first. So Actually, let's multiply by 5 first. Slightly easier. So multiply by 5. When you multiply a fraction, is the numerator the only one affected? Yeah, that's also important. So if you think about multiplication, multiplication is just repeated addition, right? So 1/8 times 4 is just equal to 1/8 plus 1/8 plus 1/8 plus 1/8. Right? And so when you're doing addition of things with the same denominator, you just add up the numerator. And so this is just equal to 4/8. So when you multiply a fraction, yes, only the numerator is affected. But then, of course, once you've converted it, when you say, yeah, 4/8, then that might be equal to something else, and you can reduce it down to just 1/2. And so that's how it affects the... yes, so the denominator is only affected during the sort of division stage of processing. Yeah, and so, like, one of the things that might be confusing, and one of the reasons I'm doing this very step-by-step, is that didn't we just add 3/8? Why did we need to do the multiplication? So we have several different steps here, right? Where was I? Multiply by 8. So when we're looking here, right? So what we have is that this here is we're multiplying everything by 8. Why did we have to do the multiplication? Yeah, so you wouldn't have to for this particular step. I was just giving an example of that. So here we've multiplied by 8 because we want to get rid of the fractions in the bottom. You don't have to do that, but that's one way of doing it. And when we do that, we multiply everything by 8. And so when you multiply 4/8 by 8, you just end up with 4. But when you multiply 3x over 10, you get 24 over 10. X. Now we've multiplied by 5, so that gives us 20x minus 12x is equal to 20. And this we can simplify to 8x is equal to 20. And if you divide, that's x is equal to 20 over 8, which happens to be equal to 5 over 2. And you can sort of see this by multiply using the biggest denominator. Oh, so I did that using 2 steps. Yeah, so there are a number of different ways you can solve this. And one is, if you multiply by the biggest denominator, multiplying by the biggest denominator is probably easier. But whichever way you multiply, you should end up with the same answer. So instead of multiplying by 8, you could have multiplied by 10 here. And that would also have worked. Because then you eventually do more multiplications and it'll all work out. The key is just to multiply enough stuff. Okay. Yeah, so if that is still confused, like there are a number of different ways of multiplying fractions. And they all should get you the same answer. So long as every operation you do, this adding or subtracting or multiplying, so long as you do legal operations, which means, importantly, don't divide by 0. So notice here, we divided by 8. But you can't divide by 0. So if you make sure you don't divide by 0, and then you can add, subtract, multiply all these things, and so long as you do all your steps correctly, you should end up with the right answer. Okay, and let me finish off quickly with just a brief mention of decimals. So note that finite decimal numbers can be thought of as a fraction over 1, 10, 100, 1,000, 10,000, and so on. So these are the powers of 10, but we haven't invented powers yet, so we can't really say that. So 1.1415 is 1,415 over 1,000. Or you can think of this as 1 plus 4 over 10 plus 1 over 100 plus 5 over 1,000. This is one way of thinking about decimals. But most fractions don't give a finite decimal number. So like 1/3 is equal to 0.3333 repeating, right? And so this is an infinite decimal number. And properly understanding infinite decimals really requires some understanding of limits, which is rigorously done in calculus, though we can sort of approximate it with a finite decimal. So for example, 1/7 is equal to approximately 0.142857. But it's not actually equal to that. So one thing that you often do with decimals, like on your calculator, is you just approximate it to some number, and hopefully that's good enough. But properly understanding all decimals is a lot more complicated. And we might talk a little bit about that later, but for now we're going to mostly work with things. We're not going to be too rigorous about that since, well, it's pretty complicated. And with that, I will end class for today, and I will stop the recording.